Hey, if you were absent, as a lot of you were on Friday, I need you to go ahead and watch the screencast just to catch you up on the carbon cycle. Okay. So basically, carbon dioxide comprises just a tiny fraction of our atmosphere's percentage composition, but it's really important. So it's about 400 parts per million, which actually it's gone up in my lifetime. We'll talk about it later, but it's about 0.04% of the atmosphere. But it's super important because without it, there's no photosynthesis, there's no life. The world is a colder place. It's a really important molecule. Now, so carbon dioxide, and we'll just say carbon because it changes forms, right? So we'll say carbon basically moves in and out of the atmosphere a number of chemical, physical, and mechanical means. So let's just walk our way through this. Um, so let's start off with the ocean. So the ocean is the largest reservoir of carbon on the planet. It is not the atmosphere, but it's the ocean. And carbon dioxide moves into and out of the ocean depending on temperature. So if you've ever purchased a drink at a like a movie theater or something like that, they have carbon dioxide and they put pressure on water, and then the water starts to bubble. That's the carbon dioxide coming out of solution. Well, it turns out that 93% of the carbon dioxide in the world is in the ocean and it's diffused into the cold water closer to the poles. But what happens is when water warms up, it tends to come out of solution, much like your soda. If you let it sit out, after a while, you take a sip, you don't feel those bubbles anymore. That's because the carbon dioxide left it. So the ocean sort of breathes carbon dioxide in and out, mostly in. It gets in the water, and most of the water in the ocean below the surface is cold. So there's a huge store of carbon dioxide in the oceans, but some of it does at the equator tend to come out when the water warms at the surface. By the way, that was a physical process. Now let's talk about a biologic process, photosynthesis. As we said, photosynthesis basically takes carbon dioxide out of the atmosphere and then stores it in the glucose in plant cells. And so basically, carbon dioxide moves out of the atmosphere and into plants during the process of photosynthesis, but then it moves from the plant cells back into the atmosphere during the process of respiration. And remember, the only reason they engage in photosynthesis is so they can also engage in respiration. So that sort of completes a cycle. So basically, have this carbon cycle happening at its simplest form. Carbon dioxide moves into plants during photosynthesis, moves back out during respiration. I just want to say it's a much better plant I drew there, don't you think? Okay, let's keep going here. Now, combustion or the burning of material, especially plant material or oil and gasoline, is essentially the same thing as respiration. Chemically, it results in the same two products, carbon dioxide and water. So respiration takes C6H12O6, glucose, reacts it with oxygen, makes carbon dioxide and water. But if we burn, say, gasoline in a car, which is octane molecule, C8H18, it doesn't have the oxygen in it, but it's a carbon hydrogen compound. When we react it with oxygen, what does our car breathe out? Carbon dioxide and water. If coal is just pure carbon, carbon plus O2 makes CO2. So the process of burning definitely takes carbon that is not in the atmosphere and then puts it into the atmosphere. Now, one way this happens through another biologic process is decomposition. Decomposition is really just respiration, but it's respiration of non-photosynthetic organisms, non-animals. So basically, we're talking about mostly bacteria and fungi eating dead things and respiring, but it does put quite a bit of carbon dioxide into the atmosphere. So the processes that I've got people coming in, so I'm going to put a mask on, but hopefully you'll be able to still hear me. Uh, so the processes that put carbon dioxide in the atmosphere, then the biological ones would be respiration and decomposition, is just a case of that. Chemical process, burning things, fire, or a mechanical process, which just warm water pushes it into the atmosphere. Now let's just dive in a little bit deeper on what happens when carbon dioxide goes into water. Okay, so when carbon dioxide diffuses into water, first, we just have carbon dioxide and water. And there's plenty of just carbon dioxide in the water, as there is in a carbonated beverage. However, a certain component of the carbon dioxide will react with the water, forming this molecule here, H2CO3. Now, this may seem like complicated, but if you look at it, it's really quite easy because there's no balancing necessary. Basically, what I did is I took the CO2 and I added another O to it and formed the carbonate ion, and then the H2 is still H2. So I'm just basically making a mashup of these. But what's important is this is now an ion and this is an ion. And so since it's an ionic compound, it's actually called carbonic acid. And if you remember from chemistry, this was called a weak acid, which means it partially dissociates. So a lot of it will stay as H2CO3, but some of it will dissociate into hydrogen ions. And here's what's important. Some of it will dissociate into unbonded carbonate ions. All right, so we need to know this process. CO2 plus H2O makes H2CO3. H2CO3 breaks apart, liberating. Well, we're going to find out in our next unit that this is a problem, but this is something that organisms really like. Calcium carbonate. I'm sorry, carbonate is what the ion is called. So a lot of marine animals will turn into a thing called calcium carbonate in order to make their shells and skeletons. So seashells, corals, many plankton, they basically use calcium carbonate, which is right here, in order to make their shells and skeletons. So what they do is they have a biological way of bringing calcium ions, which are fairly abundant in seawater, and carbonate ions, which we just talked about, and they bring them together to form calcium carbonate, which is not water soluble. So it makes this great skeletal material for corals, and shell materials for plankton and gastropods and bivalves, clamshells. Now, what happens is when these things die, the organisms die and decompose, but their skeletons don't. So the skeletons tend to pile up on the bottom of the ocean, forming a material called limestone. And since limestone is made out of calcium carbonate, there's quite a bit of carbon stored in limestone. So it's a fairly significant uh, what we call carbon sink on our planet. So let's just go over this real quick. The process that removes carbon dioxide from the atmosphere would be photosynthesis brings it in, diffusion into the ocean is another one, and the formation of shells and corals basically take it out of the water and prevent it from going back into the atmosphere. Processes that put it back into the atmosphere include respiration including decomposers, diffusion out of the ocean when it gets a little bit warm, burning anything, especially wood, coal, oil, natural gas. And then we haven't talked about this yet, but volcanic activity also puts carbon dioxide back in the atmosphere. I'll skip that. So coal is one of the main ways that we power our society. That's how we get the energy to make electricity. And oil is turned into gasoline and natural gas, which we use for electrical generation and moving, vehicles. So let's just talk about how coal gets formed. Coal gets formed basically when trees die and they have all this carbon inside their body in the form of cellulose. They fall into swampy water that has an environment that's not conducive to supporting anaerobic bacteria that would decompose it. So what you've got is an environment where the water is fairly acidic and it is low in oxygen, and so these organisms just can't live. So the dead tree just sits at the bottom there, and over millions of years, it gets buried deeper and deeper. It gets compacted and heated in the earth, and it turns into coal. So coal has in it carbon dioxide that was brought out of the atmosphere in the carbon cycle into a plant hundreds of millions of years ago, and it's just been sitting underground ever since then. So when we burn it, then we return it to the atmosphere. Oil and natural gas are formed in a very similar way, but instead of out of trees and swamps, they're formed out of planktonic organisms in the nearshore marine environment. Now, this is showing it being like octopuses and sharks and seahorses. That's not true. It's mostly made out of plankton. Okay, phytoplankton and zooplankton. But when these organisms die, they settle at the bottom, especially near shore, where mud coming in from rivers will bury them. Again, they're put in an environment where there's nothing that can eat them. There's not enough oxygen to support decomposition, so they don't decompose. And the carbon compounds in their bodies just sits there. And again, they get compressed, they get heated, and over millions of years, they get converted into oil, what's called crude oil, which has all these compounds that we sort out to make gasoline, diesel, jet fuel, natural gas, and so on. So let's just talk about what are the various reservoirs of carbon. Where is the carbon on our planet? Okay, so of course it's in the atmosphere, but most of it is actually in seawater. And the second most abundant part of it is soil. There's a lot of decomposing material in soil. So we also have forests, fossil fuels, coal and oil and natural gas, and then limestones. That's where all of the carbon on our planet is basically residing. And so again, when we burn fossil fuels, just like if you burn a tree, a tree is say 200 years old. Some of the carbon in that tree got brought in out of the atmosphere 200 years ago, and when you burn it, you're putting it in the atmosphere today. If you do it with coal, the tree that brought that in was 300 million years ago, and now you're releasing it. So basically, the burning of fossil fuels releases a significant amount of carbon dioxide into the atmosphere. Now, we sometimes divide up the carbon cycle into the fast cycle and the slow carbon cycle, and it's as simple as this. The fast carbon cycle is any cycling of carbon that does not involve plate tectonics. So it may seem weird to say that a 3,000-year-old tree is when it dies and falls down and decomposes, that's still part of the fast carbon cycle because it did not involve plate tectonics. Happens over the course of months, years, decades, centuries, millennia. But the slow carbon cycle takes much longer because it involves plate tectonic motion. Remember, we have spreading centers at the mid-ocean ridge. It moves material this way. Well, what's at the bottom of the ocean? Among other things, there's a lot of limestone, a lot of carbonate sediment. There's oil, coal, natural gas trapped in there as well. And the slow movement of this ocean rock down in a subduction zone will cause it to eventually melt, and then the carbon that's present in the limestone, in the coal, in the oil, the natural gas will get turned into carbon dioxide. And when volcanoes erupt, they'll put that carbon dioxide back into the atmosphere, completing the cycle. All right, that's it. Thanks for watching, and I'll see you in class tomorrow.